All right, let's have a look at page 29B for one more review problem. What we got here, this is page 29B. It's a homework problem. It's 352. We've got this disk that's going to roll down this ramp. The disk has a radius of 0.15 meters. Okay, and then we've got some coefficients of friction here in the mass. The mass is 1.8 kilograms. Looks like these coefficients of friction have changed a little bit, so maybe I need to revise those. That looks to be 0.40 and then 0.35. All right, so there we go. So let's draw up a free body diagram of the disk. Okay, so why don't you just take a minute and see if you can do that. So let's just get the basic information on here that we're going to need to solve this thing. What we want to do, we're just going to let this thing roll. It's going to start from rest. And we want to find the velocity of the disk when t is 2.4 seconds. We're going to assume it doesn't slip. And you're given, the mass and the radius of the disk and the coefficients of friction. So why don't you go ahead and draw a free body diagram of that disk. Let's start with that. And why don't you pause the recording for a minute and go ahead and do that. Okay. All right, so hopefully you've paused it and then you did that. Now we're going to have a look. So let's see what we got. We're going to have the weight of the disk that pushes straight down. And we can get these values here. Okay, so the weight is 17.66 newtons. Now we're going to have a normal force of the ramp on the disk, and then we're going to have a frictional force, like so. And then what we're also going to have is the acceleration of the disk, and then alpha, okay? So that would be a simple free body diagram that we would start with that didn't really require too much calculation just yet. And that would be our starting point. All right, now once you have that, there's actually two ways we've gone through to handle these rolling problems, two types of equation sets or approaches you can take on it. So for the next step here on this, why don't you write down these two methods, okay? And just write down the equations you would use. And there's two methods you could use. The first one has two equations, and the other one is a single equation that you could use to solve this. So why don't you just write down those equations, just pause the recording and write them down, then we'll take a look, okay? All right, so here's, so hopefully you've paused and gave that some thought and came up with some equations, and here they are. So if you've got an object that's rolling, you've basically got two approaches to take on it. Now, first thing, we have no slipping, so we have A equals R alpha here. Now, we can take two approaches. One is you can do two equations, F equals MA and MG equals IG alpha, okay? Now, A and alpha are related. They're not separate variables. They're related, so there's the relationship between them. So that's one approach you can take, and that's kind of a simpler approach on writing the equations. It's also to me, it's a more intuitive approach once you start to understand dynamics a little bit, that those two things are happening. Now, the disadvantage of that approach is you'll have two equations and two unknowns. So there's another way you can do it too, and that's what's down below. And this equation here is not quite so intuitive, but it's only one equation with one unknown, because by choosing where you take moments about, you can eliminate the friction from the relationship. Okay. I should mention too that we're setting up axes like this, parallel and normal to the ramp. That's the normal way to solve these. Okay, so what you would do then is you would, for the lower approach there, you would pick a point that we call A, and that would be right down here. And the intent of using that point is the friction goes right through A and causes no moment about the for the disk about point A. So you can eliminate the friction from the equation by choosing that point. Okay, so you could use either approach. And I'm hoping that by the time you take the final, you know this about things that are rolling, and that you can kind of set up this approach and be good to go with it. Once you have that thing set up, then you can start doing all the calculations and plugging the stuff in. But it is important on these different problem types that you know how to approach them. Okay, so why don't you pause here and see if you can plug some numbers into these things. You probably want to find the normal force, although that really doesn't affect the motion directly. And you probably want to get that 17.66 broken up into components along the different parallel and normal to the ramp. So maybe go ahead and do that and just see what you can do with these two equations, and then we'll run through the solution on this, okay? So you could give this a run, pause the recording, give this a run, and come back and see what we got. All right, so let's have a look. Hopefully you've given this a run and you've developed these equations. Let's see how we can do this, okay? Now we got to do all the basic information, and I'm doing that here. So I found the moment of inertia. It's 1/2 mr squared for a circular disk. So plug in the numbers, and I got the moment of inertia about the center of gravity. It's 0.02025 kilogram meters squared. Of course, we got the weight at 17.66. Then we do the trig on the weight and get that broken up into components. And I've got that shown here, okay? All right, and then we could do sum of Fy prime, solve for the normal. It's 15.59. And then I could use the fact, if no slipping, that A is R alpha. So if that's the case, alpha is A over R, which would be A over 1.5 or 0.15, which is the radius there. And that would be alpha is 6.67A. Okay, so that's kind of the basic information that I start with. All right, now once I've got that, I can take my two approaches to solving this thing. So here's the first approach. Okay, so what I've got is I would start with F equals ma down the ramp. So the force that's driving this is the component of the weight, but the friction will push back against that. The friction is going to undercut this disk. This disk is just freely rolling down the ramp. It's trying to slide down the ramp, and it rolls because the friction undercuts it. So the friction will go up the ramp, so that's subtracted, and the signs are going to matter on this, so you do want to pay attention which way things are going. So we have the component of the weight positive, the friction negative, and that's going to equal the mass, 1.8 times the unknown acceleration. So what I do with that is I solve it for the force of friction and get that expression. Then I can run my second equation at this, sum of mg. Okay, so I'm going to take moments about the center of gravity there, the middle of the disk. And what's going to cause the moment there is the radius of the disk times the force of friction. Okay, now I'm calling clockwise positive on this one because the thing's rolling clockwise, so I just do that so I have all positives here. And I will set that equal to the I sub g that I calculated, which is 0.02025, times the unknown alpha. Then I can plug in 6.67a in for alpha. Multiplying the 0.02025 times the 6.67, I get this expression here. 0.15 force of friction is 0.135a. Divide through by 0.15, and I get force of friction is 0.9a. So what I can do is take these two equations and equate them together. I've solved them both for the force of friction. So I can say 8.29 minus 1.8a is equal to 0.9a, and then I can solve for a and get 3.07. So that's method number one, you might say. Okay. So now I got the acceleration. I can find the velocity there pretty quickly when I need that. Now that is, again, the equations, if you understand dynamics, which I understand takes some time and some effort and all that. But once you get comfortable with these, they're fairly straightforward to set up. It's just F equals ma and m equals ig alpha. Okay, that's it. You do have to do the two equations to unknowns to solve it. Now, another way to do it, this is a second method, is you can set it up with one equation, like so. And what you're going to do is you're going to call point A down here. That's where the friction acts. Okay. And if that's the case, then you're going to eliminate friction from the equation. You can do this with one equation with one unknown. So what's going to cause the moment about A is this component of the weight, clockwise positive. That'll be that component of the weight, the 8.29 times the radius, which is the moment arm right there. I've got that as 1.5, but I think that's a typo. I think it's 0.15 is what that is. So let's get that fixed. So that'd be 0.15 there. And that, so that didn't write in very cleanly, but I think I've said it enough times there. So there we go, 0.15. All right, so that would be the moment. And that's going to equal Ig alpha, which is 0.02025 times alpha. Alpha is 6.67A. Okay, then plus MAGX. So the mass is 1.8. I've got A in there for AGX, and then Y bar is 0.15. All right, so I've got one equation there, and I've just got one unknown, the acceleration, so I can go ahead and solve for that. And then once I have that acceleration solved out, I can plug it into this equation here, and I can find the velocity. All right. And, we went through an example on the homework to check the no slipping assumption. I didn't include this on this one, but you can refer to that problem there. You would take the normal, multiply it by mu sub s, and then compare that. That would get you the maximum possible force of friction, and then go ahead and look at the actual force of friction. So I guess we could run through that real quick if I've got any place to put this stuff. Oh, here we go. It looks like I did it. So let's go ahead and run through that. So to check slipping, what we have here is the force of friction up here. Okay, we developed the equation here from the first approach, okay, where we looked at mg equals Ig alpha. Okay, we could have also done it from this equation, but we do have to take one of the equations from this first approach to solve for the actual friction, okay? So you plug in A and solve for the friction. You could use either one of those equations. Either one's fine. I used the lower one because it's simpler. And what I have here for the actual force of friction is it's 2.76. So that's the friction that's needed to get A and alpha to move at those rates and correspond. Now the maximum possible friction then would be the static friction, because with no slipping, we've got a zero velocity down here on the bottom of the disk, times the normal, which we solve for, it's 15.59. And this gets us the maximum possible friction, which is 6.24. The maximum possible is greater than the actual, so slipping would not occur on this. All right, so that would be the approach to use on this problem.